Welcome to presentation number 5. The agenda for today is going to be the internal interrupt framework. So far, I've talked about the microcontroller control framework, which is layer 1, and also from layer 2, I've talked about the I/O port framework. Today, we're going to continue with layer 2, and we're going to talk about the interrupt internal framework. Let's start with the definitions of interrupts. An interrupt is a signal sent by the processor that temporarily halts the normal execution of the program and directs the processor to a specific routine known as the interrupt service routine. Interrupts enable the processor to promptly respond to an event or condition demanding immediate attention, eliminating the need for continuous checking in a busy wait loop. So let's go to the data sheet and see what we can find there. As usual, let's start by referring to the data sheet. Now, as I noted before, this data sheet is organized by functionality. So let's now navigate to the interrupt section. As you can see, the first item we find is a table listing the microcontroller functions capable of triggering interrupts. There are what this is telling us is that there are exactly 24 functions that can trigger interrupt. This table also contains information needed for setting up the interrupt service routines, the ISR. So now let's jump to the register description. There is only one register which deals with the microcontroller control. The reason there is no additional information is because the detailed information on configuring each microcontroller function register to trigger interrupts are contained in each specific sections. As we navigate through each function, we will be talking about how to configure interrupts. Now this shows the same table from the data sheet, and I've added a separate column, which is the ISR, that stands for interrupt service routine, open parenthesis, vector name. Vector name is the information is going to go in this column and then close parenthesis. This is going to be the header for the ISR routine in our program. What we have in this table is the vector number, program address, source, and interrupt definition. Now this information is used to create macros, and the compiler does that for you, and the result of the macros is what I'm going to show you in the ISR vector name column. Now the interrupts shown here are the ones that are the internal, so that's why we start with vector number 7. So let's get going. So we have the Watchdog Timer interrupt. Next, the timer 2 compare interrupt, timer 1 compare interrupt, and timer 0 compare interrupt. Now, as I go through this table, it's also going to give you an idea of exactly what functions of the microcontroller have the interrupt capability. Now we have here timer 2 compare interrupt, timer 1 and timer 0 compare interrupt. And also I would like to note that after I'm done with this table, I'll explain, give you a little idea of how these interrupts work. Next we have the timer 2 overflow interrupt, timer 1 overflow. Now, and finally with the timers we have the timer 0 overflow. Next we have the SPI complete interrupt, UART receive completed, UART data register empty, UART transmission complete, analog to digital conversion complete, EEPROM ready, analog comparator. Then the last two are going to be the I2C interrupt, and then finally the store program memory ready interrupt. So let's go through each of these functions and understand a little bit about what they do. So let's start with the Watchdog Timer. Interrupt occurs when the Watchdog Timer overflows. The corresponding ISR can be used to perform specific actions when this happens. So if you let the Watchdog expire, you can configure it to basically go to a interrupt service routine, or to reset your system, or do both. In this case, we would set up for it to do a interrupt service routine, and there we would put some kind of a message if for some reason the Watchdog Timer winds down. Now let's look at the timers. Timer compares. So this trigger when the timer counter value matches the store value in the output compare register. So you have a register where you put a value, and when the timer reaches that value, then the interrupt gets triggered. This allows for precise timing operations, such as generating periodic interrupts at specific intervals. Commonly used for tasks that require precise timing, such as creating delays, generating pulse width modulation signals, or triggering action at regular intervals. Now here we have the timer 0, 1, 2 overflow. It is triggered when the timer counter overflows, meaning that the timer counter counts up to its maximum value and it rolls over to 0. So you put a value on your timer, how far it's supposed to count, and when it gets to the end and rolls over, that triggers an interrupt. It is used to perform actions that at regular intervals based on overflow of timing counter. It is useful for tasks that need to execute periodically. Common use for timekeeping and creating periodic interrupts. Now let's look at the SPI data transfer complete. The SPI interrupt indicates that the data transfer of the SPI bus has been completed. Commonly used in SPI communications to handle tasks that need to occur immediately after the data transfer is completed, such as reading incoming data, sending the next byte, or performing other data processing tasks. Now, next comes the UART receive. This interrupt is triggered when the UART receives a complete byte of data. Commonly used in serial communications to handle incoming data efficiently, such as reading data from a sensor, receiving commands from a computer, or communicating with other microcontrollers. UART U3 indicates that the transmit buffer is empty and ready for accept new data. This is used to manage the transmission of data efficiently, ensuring that the UART can send data continuously without delay. Particularly useful for implementing non-blocking transmission. So you put your data in the buffer, then you go away, do whatever you need to do, and then interrupt is triggered, this time to put more data on the buffer. So you don't have to wait for the thing to be empty. UART transmit vector. Triggered when the transmission of a byte is completed, meaning the entire frame, including the stub bits, has been sent. Commonly used in serial communications to manage the flow of outgoing data, ensuring data integrity, handle post-transmission tasks efficiently. ADC complete. The ADC finished converting an analog input to a digital value. The ADC interrupt is triggered. So you read an analog value, but then it takes some time to convert it from analog to digital. And when that task is done, the interrupt triggers, means that you can go and check your data. Allows the programmer to process the converted digital value immediately. Used in applications that are monitoring analog signals, such as temperature sensors, pressure sensors, motion sensors, and light sensors. EEPROM. Triggered when an EEPROM write operation is completed, allowing the program to proceed with tasks that depend on the completion of the EEPROM write. Useful for managing data store operations without blocking the main program execution. Used in applications that require non-volatile storage. For example, we have if you store calibration data, logging data, or other persistent data storage. Analog comparator. Trigger when the analog comparator detects a change in the comparison results between two analog input signals. The analog comparator interrupt indicates that the voltage on the positive input has crossed the voltage on the negative input. This is used for tasks that require precise voltage monitoring and comparison. TWI vector, that's your I2C bus, allows the microcontroller to respond promptly to events occurring on the TWI bus. For example, we have a successful data transfer, errors in communication, a specific condition requiring attention from the CPU. Programmers use the TWI interrupt to manage TWI communications effectively. So you have your communications through your I2C, and then if something goes wrong, you have a trigger, an interrupt is triggered, then you can go and resolve the issue. SPM ready interrupt. Interrupt vector associated with the SPM, Store Program Memory module. This interrupt vector is triggered when the flash memory write operation has completed. It indicates that the flash memory is ready for the next operation. Now, this is the program. This is what I wanted to conclude with this, showing this program. So you would have your include up here in the tab. Next, these lines represents all your program initialization, interrupt initializations, and so forth and so on. Next follows the main routine. You have your main routine, your while loop with all the lines of code, and then this is where the main ends. After your main routine ends, that's where you put your interrupt service routine ISR. So here you would have the word ISR open parentheses, then you would put this line of code from the table that I showed you for specific functionality, and here you would close the parentheses. Then you open your bracket and you write your service routine, and then interrupt service routine, and then you close your bracket. So the way this works is as follows. You're running your program here, and something happens that triggers interrupt. Immediately the program goes to this routine, to the interrupt service routine. It runs this routine, and then it's going to go back to the next line of code where you left. So finally we got to the end of presentation 5. So I talked about the internal interrupt framework. It showed you all the different functions that have interrupt capability, and went through a little explanation exactly what triggered the interrupt. And finally I showed you a program and showed you the location where the interrupt service routine would go. So anyhow, I hope you've enjoyed this presentation, and hope to see you in the next one. Thank you very much.